Oh, yeah. In this lesson, we're going to dive into some very cool manipulations of integrands. And that's what this chapter is all about, right? How to manipulate integrals. We just came off of learning about integration by parts and how to manipulate an integral into a couple of different parts. This is sort of similar in that we are going to manipulate the integral into pieces, but it's when the integrand has a fraction involved, specifically when the denominator is factorable. And I wrote that here. Anytime an integrand has a denominator that can factor or be factored, partial fractions is in the running to be utilized. What does that mean? Well, we look at this and we say, oh, I can't integrate that as is. I mean, if there was an x up here, I could use u substitution, but there isn't. So what do? What I do is I look at this thing and think, well, I could factor this into 1 over x minus 2 times x plus 2 like so. And our goal is, if only we could split this thing up into some constant a over x minus 2 plus some constant value b over x plus 2. If we can do that, then we can integrate each of these. So we're rewriting 1 over x squared minus 4, which is this, into two separate fractions, which we can do. You can split up any fraction, really. And so when we do that, we'll then have manipulated things to be able to integrate it. So without any further ado, how do we do this process? Well, the first thing that we do is, once we set up what we want, we multiply through both sides by the common denominator. That would be x minus 2 times x plus 2. All right, so we multiply through everything by that. And once we do that, you're essentially distributing this to each term, right? It goes to every single term. And so you'll get x minus 2 times x plus 2 over x minus 2 times x plus 2. This over that is 1. Just the numerators left. X minus 2 times x plus 2 times a. The x minus 2's will divide out. You're multiplying a by this. So you're left with a times x plus 2. But again, the x minus 2's will have divided out. Here, we'll multiply this by b, and the x plus 2's will divide out, leaving us with b times x minus 2. And if you don't quite see that, what I'm going to do is I'm going to write just in tiny little light blue all of what we're multiplying by. And what you'll see is why things divide out. So x minus 2 times the x plus 2 and everything. You see that these factors divide out, leaving you with the original numerator. The x minus 2's divide out, leaving you with a times x plus 2. And the x plus 2's divide out, leaving you with the b times x minus 2. Now, how do we solve something like this? Now, a and b are constant no matter what you choose for x, including x values that we technically can't plug into the original equation. A is still whatever it is. So I'm going to plug in what would make this disappear. We're solving for a and b is what we care for. I'm going to let x equal negative 2. So let x equal negative 2. This is going to go to 0. Negative 2 plus 2 is 0. We're left with 1 equals 0 plus b times negative 4. Negative 2 minus 2 is that negative 4. Then you solve by dividing both sides by negative 4. You get negative 1/4 equals b. Nice. So your b value is negative 1/4. We're going to do the same thing, but now get rid of b. So let x equal to 2. We're doing that because it'll zero this out. 2 minus 2 is 0. We'll get 1 equals 2 plus 2 is 4a. So divide both sides by 4, I get a equals 1/4. Also awesome. Now, make sure that when you plug these numbers back in, they're into the proper spots. So all of this means, and I'm going to kind of just separate this out because we didn't do any calculus here, but all of this means that we have rewritten our integral. So the integral of 1 over x squared minus 4, the original integral, is equal to 1/4 over, that's a, x minus 2. So the integral of 1/4, which I'll factor out, 1 over x minus 2. All I did there, guys, is I took the 1/4 and I factored it out. That was the a value. Then, you know what? Maybe I won't do that. I don't want to skip steps here. I'm going to put the 1/4 right in there. That's your a. Plus the integral, we're separating into two parts, of negative 1/4 over x plus 2. That's it. You have now rewritten your integral so that we can integrate both of those. And they're actually easy integrals to take. So now that we've split it up and this is equivalent to that, now what we can do is integrate each. That'll be 1/4 the ln of the absolute value of x minus 2. This will be plus a minus, so minus 1/4 ln of the absolute value of x plus 2 plus c. And it's okay to leave your answer like that. This is good. Some teachers will want you to use the log rules. So to go over those log rules, you're going to want to check out Chapter 5. I went over those in detail. So that's going to be ln of x minus 2 to the 1/4 minus ln of x plus 2 to the 1/4. And now the minus means we can divide, so it's going to be ln of x minus 2 over x plus 2, all in the absolute value, to the 1/4 plus c. You don't have to do this, right? You can go right to here, but you should know your log rules in case your teacher or professor wants you to get down there. That's it. Separate the fractions. That's the new part. The integration is actually the old part. All right, I've got one more for you. What happens when we've got an x value in the numerator? How do we deal with it? Well, these are called non-repeating linear factors, and I didn't mention that in the last one, but that's what they are. In that these factors here, the x minus 2 and x plus 2, are linear, and they're not the same, so they're non-repeating linear factors. So with this one, we do the same thing. We notice this could be factored. U substitution is not going to work. So I'll write it as 2x plus 1 all over, factor it out, x times x squared plus 5x minus 14. And we're going to split that up a little bit more. That's the same as 2x plus 1 over, make sure that equal sign's there, over x times, oh, we got 3 factors here. What's that going to do? X, this has to be a plus 7 and a minus 2. So now we have 3 factors that we know we're going to split this up into, so 3 separate integrals eventually. So this is equal to a over x plus some constant b over x plus 7 plus some constant c over x minus 2. It does not matter which letter you put over which factor, as long as we split them into 3, count them 3, linear factors. Now we're going to do like we did last time. We're going to multiply through both sides of this equation by that denominator. That's going to clear out everything, bring everything into the numerators. All right, when I do that, things will cancel. Now, the entire denominator here will cancel. That times this cancels all of it out. You're left with 2x plus 1 on the left is equal to. When you multiply all of this by a, the x's will cancel out, but you're left with a times x plus 7 times x minus 2. Not bad. When we multiply this by that, the x plus 7's will divide out, but you're left with b times x and x minus 2, the 2 factors that that denominator did not have. Not bad. And then when you multiply c over x minus 2 by that, the x minus 2's divide out, and you're left with x times x plus 7. Nice. Nice, nice, nice. Now from here, what we're going to do is, we're going to do like we did before and cancel out the other 2 values and solve for the one that remains. So I'll let x, we'll do some mental math here, equal -7. That's going to take care of the a value, that goes to 0, and the c value, -7 plus 7 is 0, so they're out. But what we're left with is -7 times 2 is -14, plus 1 is -13, and then we're left with -7 times -7 minus 2. That's -7 times -9, or 63. Ugh, that's a bad fraction. So b equals -13/63. Not nice, but again, -7, -7, multiply it out gives us 63. Gnarly in terms of a fraction, but we got this. Now we're going to let x equal another value that will zero out. Let's let x equal 0. That will zero out this and that. So these are now gone. You're left with that. That's 0 plus 1 is 1. Plugging in for x. Every x gets that 0. It's just that these cancel. X equals 0. You're going to get 7 times a -2 is a -14a. Of course, why not -1/14? Ugh, equals a. So we've got those values there. I promise you, though, the antiderivatives are actually easy. It's the algebra that takes time. Then we've got to cancel out x minus 2 because it's in those two, so we'll let x equal to 2. So the 2 times 2 is 4 plus 1 is 5. Nice. 2 minus 2 is 0. That cancels. Same here. Cancels. 2 times 2 plus 7 is 2 times 9 is 18. So c is going to be equal to 5/18. All right, none of those fractions are good. But here's the point. A is now negative 1/14. B is now negative 13/63. C is now 5/18. And while it might look like a lot of math, all we are doing here is we're selecting the x values that will zero these terms out, each of them, and leave us with one of either A, B, or C. And it doesn't matter what you plug in for x, because what you'll be left with is a constant value in the end of the day. So now what we do is we integrate each of those. So this integral is now equal to the integral of negative 1/14, right, times 1 over x. So it might be easier if I write it. Let me undo that right there. Negative 1/14 over x dx plus a negative 13/63. And as gross as that number is, it's over x plus 7. It's actually very easy to integrate. Dx plus the integral of 5/18 over x minus 2 dx. Sorry, that got a little sloppy. You're integrating those. So when you integrate this, it's negative 1/14. The integral of 1 over x is just ln of the absolute value of x. And we are not simplifying these natural logs. Heck no. This is just minus 13/63. That coefficient's hanging out. Ln of x plus 7. That's easy. And if you need a review of your natural log integrals, go back again to chapter 5. Plus 5/18 ln of x minus 2 plus c. Oh! The actual integration of integration with partial fractions is easy. The integration part is not bad. And that's the point, is that we want to manipulate things so the integration is simpler. When you look to break things into partial fractions, you literally just are looking to see, can I factor it? And if so, do it. And again, look for the x values that will zero out as much as you can. Plug in that x value into the other terms that don't zero out and solve. And then you'll have your nice manipulated integrals with some nasty fractions, albeit, but nice antiderivatives. All right, that's it. Fun stuff. I'll see you in the next video. We'll go over some different varieties of partial fraction decomposition. Peace.